Hello everyone, I'm Jesse Mason, and for this edition of Teach Me, we're going to use Kirchhoff's rules to analyze a circuit. Specifically, we're going to determine the current through, the voltage across, and the power dissipated by the two resistors that you see here. As always, when using Kirchhoff's rules, we're going to start by labeling our junctions. I'm going to label mine J1 and J2. Next, we label our currents. I'm going to label this current I0. After junction 1, I'll have I1 on the right leg. Note that I0 does not pass through junction 1. This middle leg will be I2. And when I1 and I2 rejoin, we have I0, because the current coming out of that 1.5 volt battery needs to be the current coming back in. Also note that the directions of these currents at this point are arbitrary. We'll find out if we chose the right directions after we complete the problem. Next, we label our loops. I'll label this loop A and this loop B. Just like the currents, the direction of your loops is arbitrary. And you can label this outer perimeter loop C if you'd like. I'm not going to. I anticipate we won't need it. Now that we've labeled our circuit, we're going to apply the junction rule. The junction rule states that the sum of the currents into a junction is equal to the sum of the currents out of a junction. So we're going to apply this to junction 1, and the currents in is just I0. So on the left-hand side of the equation, I'm going to write I0. And the currents coming out of that junction, we have I1 here, and I2 here. So on the right side of the equation, we'll have I1 plus I2. This junction rule, by the way, is just a consequence of the conservation of charge. Now, if I apply the junction rule to junction 2, we'll have I1 coming in as well as I2 coming in. So on the left-hand side of the equation, it would be I1 plus I2. And we have I0 coming out. So on the right side, we have I0. This is exactly what we have already written. So we're not going to use that equation. Now we apply the loop rule to loop A, which states that the sum of the voltages around a closed loop is equal to 0. Starting in the upper left-hand corner, we're going to move clockwise around loop A. And the first component we get to is the 100 ohm resistor. Now here we're traveling clockwise, so we're coming down this leg, moving with the direction of the current. This means we're going to have a voltage drop across the resistor, negative IR. So I'm going to write negative I2 times 100 ohms. To indicate the voltage drop. And we continue to move clockwise around loop A until we get to our next component, which is the 1.5 volt battery. Here we're moving from low to high, negative to positive. This indicates a voltage lift, positive V. So I'm going to write plus 1.5 volts. And that's the last component in this loop, so I set it equal to 0. Next, we use the loop rule to analyze loop B. Starting again in the upper left-hand corner, we travel around clockwise until we get to the first component. It's a 9 volt battery. Traveling from high to low, that means a voltage drop, minus 9 volts. Continuing around loop B, we get to the 200 ohm resistor. We're traveling clockwise, which is with the direction of I1. That's going to indicate a voltage drop, minus IR. So I write minus I1 times 200 ohms. And then we continue around loop B up the middle leg until we get to the 100 ohm resistor. Here we're traveling up the leg, whereas the current is traveling down. This is going to indicate a voltage lift, plus IR. So I write plus I2 times 100 ohms. Complete loop B. Set this equal to 0. And at this point, the physics of determining the current in this problem is done. All that's left is some algebra. We have 3 equations, 3 unknowns. We can solve this. I'm going to start with the middle equation here. Solve for I2. Now I'm going to do something a little unorthodox for physicists. I'm going to drop the units. This is pretty much the only time I ever do this, but when using Kirchhoff's rules, it makes the equations much easier to handle, especially when they get really hairy. So this is what my equation looks like. I'm going to solve this for I2. I2 is equal to 0.015 amps, or 15 milliamps. I box this up. And now I'm going to use this value to solve for I1 in the equation above. I'm going to plug it in here and solve for I1. Again, I'm going to drop my units, rewriting the equation. By the way, if you're comfortable with linear algebra, you may want to set these equations up in a matrix and solve for the variables that way. Often that is a much simpler way of handling the algebra. In this case, I'm just going to plug and chug. So this product is equal to 1.5 volts. Move it to the other side. I have negative 200 I1 is equal to positive 7.5. So we have I1 equals 0.0375 amps. Oh, don't forget this negative sign here. That's important. Negative 0.0375 amps, or negative 37.5 milliamps. So what does this negative sign tell us? This negative sign tells us that the direction that we chose for I1 is the wrong direction. Remember how we picked it arbitrarily at the beginning of the problem? Well, here's where we find out that the actual direction of positive charge flow is the other way. No harm, no foul. Now we know the correct direction of the currents. So we're going to take I1 and I2, plug them into the junction rule to determine I0. So I0 is equal to negative 0.0375 plus 0.015. So we have I0 is equal to negative 0.0225 amps, or negative 22.5 milliamps. I'm going to box this up. And again, what this negative sign is telling us is the direction that we assigned for current is the incorrect direction of the positive charge flow. It's actually moving the other way. So now that we have the currents in this circuit, we can determine the voltage drops across the resistors using the current and the resistance values. In other words, we're going to use Ohm's law. So for current, we use the 15 milliamp value and the 100 ohm value. And we find out that the voltage drop across the 100 ohm resistor is going to be 1.5 volts. I'm going to do the same thing for the 200 ohm resistor, but to conserve some space here, I'm going to skip the calculation and just get to the value. So using that current and the 200 ohm resistor, we have a value of 7.5 volts for the voltage drop across the 200 ohm resistor. To determine the power dissipated by these resistors, we simply multiply the current through by the voltage across, IV. And we find out for the 100 ohm resistor, we're going to use the 15 milliamps for the current and the 1.5 volts we just determined. And we find out that the power dissipated by the 100 ohm resistor is going to be 0.225 watts. 22.5 milliwatts. And to determine the power dissipated by the 200 ohm resistor, we're just going to multiply the current times its resistance value, which yields 281.25 milliwatts. And I'll box this up. And we're done. So there you have it. The current through, the voltage across, and the power dissipated by resistors using Kirchhoff's rules. I'm Jesse Mason. I hope this was helpful to you. And until next time, happy learning.